Right. So, like I said, it should be EE1203. Remember, the code just changed previously, but it's still the same material and it's the correct material. So we've talked about semiconductors, how they are constructed, how we come up with N and P type semiconductors. So I'll just give you a quick preview, right? So we said the semiconductors that we use are the group 4 elements, which is the 4 outer electrons. And I was saying you would need almost the same energy to lose or gain the 4 electrons to achieve a stable octet. So instead of losing, the semiconductor tends to share with other elements. So when they are sharing, it means the electrons are still bound to their atoms, but then they are also bound by some covalent bonds to the other electrons so that they are being shared, right? So we said silicon, it needs 4 to be stable. So if you make it share electrons with a group 5 element, say phosphorus, then the 4 phosphorus electrons will make silicon become stable, and also the silicon becomes stable, but then there will be 1 extra electron which will be available to be used for conduction, right? And hence, because the electrons are in excess, we have a net negative charge. That's why when you add a group 5 element, you get an N-type semiconductor. For group 3, we said it is only 3. That means even though it shares its 3, there's still a deficiency of 1 electron. And then that deficiency of an electron will produce what we call a hole, which now gives a net positive charge. Remember, a net positive charge exists when there is a deficiency of electrons, right? So that's why we have a net positive charge when we add a group 3 element. And that group 3 element, when it is added to an intrinsic semiconductor, then that's how we get a P-type semiconductor. P meaning to say it is a net positive. And then, if you don't want to be in class, just get out of class, please. Don't disturb us. That's the warning. So I was explaining that when you add a group 3 element to an intrinsic semiconductor, silicon, then we have a deficit of electrons and we have a net positive charge in that combination. And that's what we call a P-type. So the majority carriers in the N-type will be electrons because they are the ones which are in excess. In a P-type, they are the holes which are in excess. But from the first statement that were given, you also realize that we still have electron hole pairs being formed. But the reason why those do not cause an excess is that no hole will exist without a free electron. So in other words, we have this equal number of electrons as holes when we are not doping. That's why it will always be like a neutral, right? So we now look at diodes, right? So how do we create a diode? That is what we are going to look at, right? But before we go to that, we just also want to go back a bit to look at our energy levels, where we're explaining the insulators, the semiconductor, and the conductors, right? So that's our energy diagram. The insulator, the energy gap is very large. No electron can jump to reach the conduction band, and hence it cannot conduct. Semiconductor, the energy gap is moderate, meaning to say with enough energy, in this case, thermal energy, with enough energy, an electron in the valence band in a semiconductor can jump to the conduction band. But because of that gap, it means we have fewer electrons which can actually jump to that level, right? Then in conductor, in our case, we are specifying about metallic conductors. The covalence bands and the valence bands overlap, meaning to say there are electrons whose energy level fits for the conduction in the valence band. In other words, that is why metals can easily conduct, because they have a pool of free electrons that already have enough energy to move, right? So when you look at intrinsic semiconductors, in other words, in semiconductor which has not been doped, for example, pure silicon, we have thermal excitation, whereby we are giving energy to an electron so that it can jump to the conduction band. When the electron jumps to the conduction band, we are creating an electron hole pair, right? But then when the electron falls back into the valence band, we have what we call recombination, that is, the hole is cancelled. And this happens and we achieve what we call equilibrium, right? So we're looking at electrons jumping to the conduction band, leaving a hole and creating a free electron. And then they can also jump back and cause recombination, right? So when this thing occurs, that's what we call an electron hole pair. One hole, one free electron, right? When we give a heat, it is only the heat which can allow this to break out there and get into the conduction band, right? So in the actual lattice structure, we can visualize it like this for an intrinsic. So generally we are saying every silicon atom, okay, let me use this one. Every silicon atom is surrounded by 4 silicon atoms so that it can share its electrons to achieve stability. And then the next one will also have its 4 surrounding it to achieve stability, and so on and so on. And when we give heat, right, the electrons have enough energy to move out of the bond and participate in conduction. When they lose that energy, they fall back to the bond, and we have what we call recombination, right? So if you apply a voltage across silicon, there is electron current and hole current, right? What does that mean? Our electron is negatively charged, so it will move towards the positive, right? When it moves towards the positive, it creates a hole, right? So let's say this electron jumps to that point, right? It creates a hole at that point, right? This electron jumps to fill that hole, it creates a hole here, and this electron jumps to fill that hole, it creates a hole here. So you read that generally there is net movement of holes to the left and net movement of electrons to the right. Okay, that's where we have electron hole current, right? This is what I was explaining. We don't have to read everything there, right? But it says first situation, electron jumps, leaves a hole, right? Then the next electron moves to fill that hole, and it leaves a hole. Then the next electron moves through that hole and it leaves a hole. So in general, it looks as if holes are moving to the left and electrons are moving to the right, right? That's what we are describing. So this is the formation of what we have as a pure silicon crystal, where it is sharing 4, 4, 4. It shares with this, it shares with that, shares with that. It achieves its stable octet, right? Then, can you please mute your mics when you get into this class? They're disturbing other things. So it shares with 4. This is now stable. This one will share with others. 1, 2, 3, and the 4th one here, it becomes stable. Then the other one shares again, and it creates its own complete lattice structure. Then we go on to N and P type semiconductors. I've explained that in the previous lecture. We use what is called doping. When we talk about doping, we're talking about the introduction of impurities into a pure semiconductor, right? So these, what we add are what we call dopants, right? For N-type, I said we add group 5, and we have these examples, right? Phosphorus, selenium, and the like. Then, when you add that dopant, here, it shares 2, that's 1, 2, 3, 4. But because it is group 5, it has 1 extra electron which is not paired to any of the silicon, and this is the one which can now participate in the conduction to create an N-type semiconductor, right? Then P-type, again, with boron and other atoms which we can use. And then this is only 3, so it can only stabilize 1, 2, and 3. This one becomes a deficit of an electron, that is a hole, and hence we have a net positive which can be used for conduction, right? Then we have the PN junction. Now, a P-type semiconductor on its own is not very useful, and an N-type semiconductor on its own is not very useful. But when we combine them, then we start talking about electronic devices, right? So the basic electronic device, whichever you will meet, is basically constructed using this basic theory of a PN junction. So how do you construct a PN junction? So at first, you have an intrinsic semiconductor material, your silicon, right? Now, what happens now is you start building in any type on this side by diffusing a group 5 elements or a dopant. And on this side, you start creating a P-type by diffusing a group 3 element there. So the P will grow in that direction and the N will grow in that direction. Then these two will meet at a certain point, right? Where you have a net N-type on this side and a net P-type there. What is created here becomes the PN junction. Simple English, P and N. junction, right? So on the N side, we have more electrons. On the P side, we have more holes, right? I'm saying more because there's no way you can have holes, all holes. Why? Because when you are doping, we are introducing a certain percentage of impurities, meaning to say a certain percentage of the intrinsic will still remain. So at the instant of junction formation, the free electrons in the N region near the PN junction begin to diffuse across the junction and fall into the holes near the junction in the P region. So some electrons will jump, neutralize the holes on that side, right? And what happens? They also create a deficit of electrons where they are living. Okay. Then as this continues, you realize that those electrons which are jumping across the junction will end up causing a net negative charge there, right? Because they were jumping from here to there, they were leaving holes, and then we have a net positive charge on that side. So this is where we should understand how this whole thing works. Because if we don't understand it here, then we are going to get into problems. You should understand that when you have a P side and an N side, the P side is net positive because of the holes. The N side is N net negative because of the electrons. But when these two combine at the junction, right, electrons will jump across the junction to the P side. And at the end, we're talking about what happens near the junction. We have a net negative on that side, on the left with the P side, and a net positive on the N side at or near the junction, right? In other words, at this point, you have a positive here and a negative there on your P-N junction. This is not overall, but that is what happens at the junction when you achieve equilibrium, right? So for every electron that diffuses across the junction and combines with the hole, positive charge is left in the N region, and the negative charge is created in the P region, forming what we call the barrier potential. This action will continue until the voltage of the barrier repels further diffusion. What are we saying? By saying as the negative builds up, there comes a time when no more negative can cross. Remember, negative charges will repel. So if you get more negatives on the P side, then there's a time when no more negatives can cross, and that creates our barrier potential. Now, because we have a positive and negative, it means we have a voltage which is now existing across the junction. I'm being slow because this is the most important part which you should understand for you to later on understand what happens in our semiconductor material. Right. Then go on to the depletion region. So the concentration gradient causes the electron to diffuse from the N to the P, and the holes diffuse from P to N. Remember, we said a hole is created by the movement of an electron. This produces immobile ions in the vicinity of the boundary. That is what I was explaining in the previous diagram. So at the junction, the region at the junction with charged ions is called the depletion region or space charge region, right? Why depletion? Because in that region, we have depleted holes on this side, and we have depleted electrons on on that side, right? So holes diffuse to that side, electrons diffuse that side. Remember, we said a hole is created by the movement of an electron. Let's try to visualize that. So we have hole drift, current, and electron drift current in that case. So charges create electric field that attract the minority carriers, causing them to drift. Okay. So what does that mean? Because of that net negative that is there now, some minority carriers would tend to drift towards them. In our case, the minority on this side are the holes, so they tend to move there because of the charge. And the minorities on the P are the electrons, so they will also tend to drift due to that current. So drift counteracts diffusion, causing equilibrium. Right? In other words, after the formation of this, we are saying we are not saying that when this region is formed, there is no more movement, but we are saying whatever is diffusing there is also now being cancelled by what is drifting in that case. Okay. So again, we've just explained what happens when we have not connected this setup to a source. So as it is, again, needless to say, it's also useless in terms of our electric circuits. But it helps you to understand what happens when you now connect a source. So there's no movement of charge through the PN junction at equilibrium. In other words, what moves to the left is the same as that moves to the right, so there's no net movement of charge. So the PN junction will now form a diode which allows current in only one direction and prevent current in the other direction as determined by the bias. So what are we doing when we are biasing? We are trying to force current to move in a certain direction, right? So that is our circuit symbol for the diode. This is our circuit symbol for the diode, right? So the arrow shows the direction of movement of conventional current in forward bias. We'll talk about that later, okay? So this is the physical presentation of our PN junction, right? The junction is there, but this is the electrical symbol or the circuit symbol for our diode. And the voltage drop across the diode is determined by the barrier potential, which we're explaining. That means when there is net negative on this side and net positive on this side, there's a certain voltage which can be measured here. This is the diode voltage that we are talking about. So we have two ways of biasing. The first one is called the forward bias, right? So when I'm saying the forward bias, we are saying if we were to look at the circuit symbol of our diode, remember we said the diode circuit symbol is like this. And then the arrow in the diode shows the direction of current. So if you connect a circuit side that current can move in this direction through the diode, then you are forward biasing it. Now, how do you achieve forward biasing? So when you are forward biasing, you use a DC voltage, right? So the positive terminal is connected to the P side. So you connect positive on this side. And the negative terminal is connected to the N side. That is now our forward bias. Right. So what happens during forward bias? So The positive terminal or the positive potential would tend to move electrons away from there, right? So that the negative charge becomes smaller and smaller and smaller. On this side, the negative would tend to move the positive away from the barrier. And then the positive charge becomes smaller and smaller and smaller, so that at the end of the day, this becomes almost non-existent or zero, right? And hence we have forward bias, right? So we are pushing our positive in that direction and our negative in that direction. Then so this would be negative and positive there, so that, right? So as the positive increases on this side, it tends to add up to the potential of this barrier. And then at the end, the barrier will tend to disappear slowly. And hence we have forward bias, whereby this depletion region shrinks and shrinks until there's total conduction in that direction. So voltage, this voltage P region and negative to the N region, right? Then what happens? Positive will attract electrons to this side, right? So they will jump and start to neutralize everything there, right? And then the holes will also be moving in the other direction, and resultantly this becomes very, very small and it shrinks, right? Then forward bias, it means when you are looking at the circuit symbol now, we are putting our anode on that side, positive, and our cathode on that side, negative. This would be our P side and this would be our N side, that is forward bias. So when you have to graphically show the current voltage characteristic of that diode, when the voltage is negative, I think I jumped something there. Yeah. Let's wait a bit, okay. So, okay, it's fine. So we are on this side, right? Where our barrier, the voltage across this is positive. So as the voltage increases, there's a time when the voltage is approximately equal to the barrier potential, right? The depletion layer disappears, and then a large current starts to flow. I'll explain the left side when we look at reverse bias. So this is our region for forward bias. On reverse bias, the negative terminal is now connected to the P side, and the positive terminal is now connected to the what? To the N side. So we're now having a positive on that side and a negative on that side. Right? Sorry. It's a negative on this side and a positive on that side for reverse bias. So what happens here? The negative will attract the positives, right? And the positive on that side will attract the negatives. So what happens? If negative moves away from here, it leaves a positive there. Negative moves away from there, it leaves a positive, and leaves a what? A positive, right? Remember, it's a minus and a plus on the junction. So what it means is, at the end of the day, we have the negative increasing in that direction. Instead of shrinking, the depletion layer will tend to increase. So as you increase the voltage, you are also attracting more positives and creating more negatives that are left behind. So it will still adding more positives there by removing the negatives, right? And so at the end of the day, you now have a bigger positive and a bigger negative on that side. Meaning to say, as the depletion region expands, it means there is no movement of charge across the region. What can only exist is just that diffusion current, which is counteracted by the drift current. But now in this case, the drift current would be tending to move a charge away from the barrier. So at the end of the day, the depletion layer will become wide until its potential difference equals the bias voltage. And there is no majority current carriers. There's no more movement because of that expansion. So majority carrier current ceases because there is no more easy movement across the region. There's still a small current produced by the minority carriers due to the diffusion, right? That's why now, like I was explaining, that small diffusion current, which is still flowing, when there is reversed bias there. But we reach a time when the electric field intensity or strength across the junction becomes so large that it will cause the bonds to break down, right? When the bonds break down now, it will cause a movement of a large current. That is when there is breakdown. So our semiconductor is now broken down due to the electric field strength that was becoming higher and higher as the voltage increased, and hence it go to that point, right? So that is how we achieve reverse bias. Then we are just explaining the current voltage curve for a specific material there, right? Then we have what the Shockley equation, which is used to calculate the currents that can flow when you are biasing your diode, right? We don't really use this equation in this course so much, but when I'll give you the variable so that at least you can be able to just reconstruct this kind of scenario for your diode. Just shows you how you can relate the movement to temperature, but it's not very important for you to look deeper into it, at least for now. Right, so we end our lecture here, and we end it today. We'll move on as we go tomorrow. On